Let's consider the following problem. Consider an AC generator with frequency F, peak voltage V connected in series with resistor, inductor, and a capacitor. What is the resonant frequency? What is the average power at this frequency? Alright, so let's basically just consider this problem out very carefully. Let's now draw the diagram first. Let's consider this thing. It has some frequency F. It's going to be going across. It's going to be a resistor. That's going to be an inductor. That's going to be a parallel capacitor. I'm going to join everything back. Okay. So this is R, some L, some C. This is some V. Let's imagine some current I pushing everything through. Okay. And I'm going to use Kirchhoff's law to basically get this thing. So it's going to be basically V cosine of omega t. Alright, that's this thing. Minus IR minus L di dt minus Q over C is equal to 0. Alright, so I'm going to move all these things aside, leave this isolated. I'm going to get this. And I'm going to also note that I is equal to dq dt. Okay, so now let's move all this stuff to the other side. So I'm going to get basically R dq dt plus L d squared q dt squared, and then this one plus q over c is equal to v cosine of omega t. Alright, now what I'm going to do, I'm going to basically write this more like this simple damped harmonic oscillator. I'm going to divide L on all sides, and so we're going to get something that looks like this. Basically d squared q dt squared plus r over L dq dt plus 1 over LC q is equal to v over L cosine of omega t. Alright, so this is my simple damped forced harmonic oscillator. Alright, and in order to solve this problem, basically I'm going to complexify this problem first. Then I'm going to basically get out what the current is going to be. Then I'm going to get out what the power is going to be across the resistor, and then I'll calculate what the average power is going to be. Okay, so got that? Let's just do it. Okay, so in order to make this problem solvable, I'm going to complexify everything. And the way you complexify it, you look at this cosine omega t, you write it as v over L exponent I omega t. Now you could use exponent, you could e to I omega t, it doesn't matter, right? They're both the same thing. Okay, so to keep my writing to a minimum, I'm going to write this as v over L e to I omega t. Okay, this the not writing x and p and the parentheses does save a bit of time for me. Okay, so let's do this. So this is my problem. I'm going to guess my solution. The guess I'm going to put in is q is equal to some q squiggle, alright, e to I omega t, right? So plug this thing in. What I'm going to get is I'm going to get a minus omega squared q squiggle, alright, e to I omega t plus I omega q squiggle times r e to I omega t, and then plus q squiggle over LC e to I omega t. This is going to be equal to v over L e to I omega t, and now you can see the e to I omega t's will kill each other off, and then I have expression basically for q squiggle in terms of everything else. So now q squiggle is going to be equal to v over L divided by let's see now, I have this term right here, 1 over LC minus omega squared, close that up, and then I have a complex thing right there, plus I omega R, right? Okay, and then that's my q squiggle, alright? Okay, so now with this q squiggle, right, I can write down my solution. So in order to make this thing a little bit less annoying, what I'm going to do is I'm going to basically take this complex part out of the denominator and put it in the numerator. In order to do that, I have to multiply this by 1 over LC. Well, okay, we'll see. Minus omega squared minus I omega r divided by 1 over LC. We'll call it the same thing. Okay, it's the same thing. So when you multiply this thing out, what you will get is going to be basically V over L, right? Um, 1 over LC minus omega squared, entire thing squared, minus plus omega squared r squared, and then on top you get basically 1 over LC minus omega squared, close that up, minus I omega r. Alright? Okay, now it's the same trick as we did for basically question 1. What you want to do is you want to reduce this down to something that looks like a normalization times basically tangent of delta. Okay, so needless to say, you can rewrite this thing as basically Q squiggle is equal to V over L. I'm going to rewrite this thing as this is just omega naught squared now, right? So this will be simply be 1 over square root of omega naught squared minus omega squared, everything squared, plus omega squared r squared. Okay, and then on top, I'm going to rewrite this e to I delta, and delta is just going to be equal to, well, the tangent of delta is going to be equal to this thing divided by that thing. So it's going to be equal to basically omega r minus divided by omega naught squared minus omega squared. Okay, so that's delta. Alright, and so the final solution for Q is equal to Q squiggle is V over L, okay, 1 over square root of omega naught squared minus omega squared, entire thing squared, plus omega squared r squared, e to the I delta, where delta is just defines that. Okay, so once we have this, we can figure out basically what I is. I is equal to dq dt. This is going to be equal to, whoops, plus I omega t. Right? Don't forget this part here. Okay. Well, d by dt just brings out omega from this entire expression. So what you end up getting is basically v omega over L 1 over this entire square root e to I omega t plus delta. Alright? Okay, so we're going to take the real part of this guy. So what you end up getting is that this is just basically omega v over L 1 over that square root thing. This is now a cosine omega t plus delta. Okay, now this delta is the phase shift as a result of basically these extra circuit components here, namely inductor and the capacitor, right? And this basically results in phase shift. Is basically means that we don't drive wherever we drive at the frequency at omega t, the response is going to be different by some phase, all right, which we can calculate from here. All right. Okay, so now to basically get the rest of it, all right, this is my I. In order to get my average power, P average, it's basically the power dissipated across the resistor here. So this P average is just going to be I squared R averaged over a period. So average over a period, this means average over one period. So it's going to be integral of 1 over the period 0 to what's the period? T. okay, dt of I squared r. Okay, we do that. This is actually nothing too difficult. All right, let me make sure I get everything right. Everything looks good. Everything looks good. Okay, so let's plug everything in. So this thing is going to be, what we'll say. So 1 over the period is 1 over is basic frequency, which is omega over 2 pi, integral from 0 to 2 pi over omega. All right, and now I need I squared, which is just basically omega squared v squared over L squared 1 over the entire thing, which is omega naught squared minus omega squared plus omega squared r squared. Okay, that's I squared. I multiply times r on top. That's this r right there. Cosine squared omega t plus delta. Okay, and then basically dt. Okay, so here's something that everyone should know, but if you don't, it's good to learn at this point. This integral over a period of any cosine squared omega t is just basically it's just pi. Okay, sorry, it's pi over omega, or really it's 1/2 of basically 2 pi over omega. All right, so this is just pi over omega. So this integral right here just going to be pi over omega. So this is just going to be equal to, let's write this thing down. Pi over omega, we'll kill this one, 1/2, right, of omega squared v squared over L squared r divided by omega naught squared minus omega squared targeting squared plus omega squared r squared. Okay, and that's it. Okay, hope that was helpful.